and research environments. Speech contains valuable information beyond words. When scientists explain ideas, collaborate, or participate in virtual reality training scenarios, their speech can reveal confidence, hesitation, engagement, uncertainty, and emotional state. The challenge is that this information is difficult to capture at scale.
What's going on here? This is not true.
This is where Speemo comes in. Speemo is an end-to-end framework developed by Martin Khadjavian for automatic speech recognition and speech emotion recognition. It is currently in the test and use phase for integration into virtual reality learning analytics sessions at Learning Technologies at RWTH Aachen University. At the core of Speemo is a pretrained RWTH self-supervised learning backbone. This model first learns general speech representations from large amounts of raw audio and is then fine-tuned for specific tasks such as transcription and emotion classification. For ASR, Speemo fine-tunes the model to convert audio into text. For SER, it fine-tunes the system to recognize emotions such as neutral, happy, sad, angry, fear, and disgust. For English emotion recognition, Speemo uses a cross-corpus strategy. This allows the model to learn from a larger and more diverse emotional speech collection. The development of Speemo followed 2 stages. The first version, Speemo SD, was created as a local small dataset prototype. Its purpose was to prove that the complete system works end-to-end, including preprocessing, training, checkpointing, file-based inference, real-time streaming, browser-based interaction, and structured logging. Because local hardware has limited memory, Speemo SD uses parameter-efficient fine-tuning, especially LoRa adapters. This makes it possible to adapt a large pretrained model by training only small additional components instead of the full model. After the concept was validated, the system was scaled into Speemo MD, the medium dataset version. Speemo MD keeps the same general architecture, but moves training to the RWTH Aachen University HPC cluster. This was necessary because larger datasets and higher batch sizes require significantly more computational power. In this stage, the ASR models were trained with more than 30,000 audio files per language. The English SER model was also trained on more than 30,000 emotion-labeled audio files from the harmonized cross-corpus dataset. Training on the RWTH SLURM-based HPC cluster enabled stronger GPU resources, reproducible training environments, and more stable training runs. A key design decision is that the cluster is used for heavy training, while the final fine-tuned models can later be copied back and used locally for inference. In this way, Speemo combines powerful centralized training with practical local deployment. The training pipeline follows a clear structure. Audio files are resampled to 16 kHz, normalized, segmented, and prepared for training. ASR transcripts are cleaned and tokenized. SER labels are mapped into the unified emotion set. Augmentation techniques such as noise, pitch, and speed changes can improve robustness. After preprocessing, the RWTH backbone is fine-tuned separately for ASR and SER. Training is monitored through logs, checkpoints, and validation metrics such as word error rate for ASR and weighted F1 score for SER. Once training is complete, Speemo can be used for inference. In file-based inference, an audio file is processed and transformed into structured output.
Mensch, das kann doch nicht dein Ernst sein.
Including transcription, timestamps, predicted emotion, probabilities, and confidence values. In real-time inference, microphone audio is processed in overlapping windows.
What's going on here? This is not true.
The system produces incremental text and emotion predictions over time, making Speemo suitable for interactive environments such as VR-based learning analytics. The evaluation shows a clear progression. Speemo SD demonstrates that the system works locally and supports training, streaming, inference, and logging. Speemo MD improves quality and robustness by scaling training to larger datasets on the HPC cluster. At the same time, there is still room for improvement. Sentence separation, punctuation, tokenizer alignment, and language-specific characters can be refined further. The broader value of Speemo lies in what it enables. It turns spoken interaction into structured learning analytics data. These logs can help analyze participation, fluency, hesitation, turn-taking, and emotional development during a session. In virtual reality learning environments, this can support adaptive feedback, teacher dashboards, and deeper analysis of collaborative learning processes. It is a step toward emotionally aware, speech-driven learning technologies.